As you recall, the multiplication rule for independent events was the following. The probability of E and F is equal to the product of the individual probabilities of E and F. We specifically used this rule when in the scenario in a previous video where we were, for example, picking a card out of a deck. We concentrated on this entire upper quadrant here where we would replace the card, pick another card, the deck would be refreshed, and of course the events ended up being independent. So this lesson is going to concentrate on the lower avenue here, where what's going to happen is we're going to, once we pick the first card, we're going to keep it, and we're going to result in dependent events. So the multiplication rule for dependent events is not going to be too much different. I already did a little bit of hinting of it in the conditional probability section. We, of course, are still going to be finding the probability of E and F. And we still have to start with the original probability of E, but this is where things change a little bit. So the key here was that E had no probabilistic effect on F occurring. So this time, E is going to have an effect on F occurring, whether it's because of lack of replacement or some other underlying thing that changes the dependence. So this time, we are going to find the probability of F, but now we're going to be using the conditional probability that E has already occurred. The key is that this is telling us that F is going to change somehow based on the fact that E has occurred. Okay, so in summary, basically, we're going to be concentrating on this formula in this lesson, although you're not going to see a whole lot of difference in the way you proceed with things, truthfully, because it's going to be multiplication either way. All right, let's look at our first example. It says, consider a deck of 52 playing cards. Find the probability of selecting a king and then a queen without replacement. Okay, so a couple things to take note of. You see that this says without replacement. That means from the material you have already learned, we are going to have dependent events that we're dealing with. What are these events? Well, just like we have in the past, we can label them with a letter. We'll call K and Q for selecting a king and queen for what we're doing. So what is the ultimate goal of this problem? We're looking to find the probability of a king and then a queen in succession. But like I'd mentioned earlier, remember that we are not, right? We're not putting the card back. We're keeping the card out of the deck. So that's going to change a little bit of the process in which we go. So according to this should be equal to the probability of selecting a king times the probability of selecting a queen given that the king has occurred. So this basically is here in a sense to tell you that, hey, keep in mind that I can't just use the probability of a queen outright because we have taken this without replacement has changed the game a little bit, and now there's going to be a change most likely in the denominator. So what does this look like? Well, first, what's the probability of selecting a king? Well, that's not going to change. In the first selection, when we reach in the deck, we have 52 cards. And we know that there are 4 in the event of selecting a king. Okay, but this is where things are going to change a little bit. So let's say you pick a card out of that deck and you're looking at a king. You decide, well, I'm just going to keep the sucker and put it in my pocket. So the next time, when you go to reach in that deck, something's changed. It's not refreshed anymore, and it's no longer 52 cards. Now it's 51 cards. And if you're going to pick a queen, you have to decide, well, how many queens are in that deck of 51 cards? Well, luckily enough, we actually haven't taken out any queens, so there still are 4 in there. Now, if I had said pick another king, then this number up top would have been a 3 because there would have only been 3 left. But in this scenario, since we're picking a totally different card, a queen, that is not the case. If you do the mathematics for this on your calculator, you're going to get about 0.0060. All right, let's look at the next card example. It says, find the probability of selecting a heart and then another heart without replacement. So again, not going to write dependent, but because it says without replacement, we know immediately that that's going to be the case. We also want to label our events to make it easier to write. Because it says two different hearts, as we've done this in a previous video lesson, I'm going to call it H1 and H2, which means that we are looking for the probability of H1 and H2, as in the first heart and then the second heart. By the formula, because we know these are dependent events, we can say, well, this is going to be equal to the probability of picking the first heart, because that's coming from the stable, regular 52 card deck. But then we have to take into account that we're taking a card out. So we are looking for the probability of heart 2, but given that heart 1 has occurred. So what does this look like? Well, the probability of picking a heart from a full deck is just 13 hearts out of our total 52 cards. But remember, you're taking that heart and you're putting it in your pocket and you're going to pick out of the deck again. So there are only 51 cards left, but there's also only 12 hearts left when you go in there because one is in your pocket. Therefore, it's a little bit different than letter A, and we end up with 0.0588 as our probability. Okay, so this is a good time to just pause for 1 second so I'm clear about what I expect in terms of exams and such. I am not going to be overly concerned about you writing basically this section of the formula for either of these. In multiplication rule problems like this, it's perfectly fine just to get right into the business and start doing the math. It's a little bit different than the addition rule, in which the formula is so important to the process that you really have to have it there. But just jumping into the mathematics of it is perfectly fine, which is ideally what I want you to do. For example, if we do our final card here, card example scenario, it says, what's the probability of picking 3 jacks in a row? So instead of writing like J1, J2, J3, and writing J1, probability of J1 and J2, and there's no reason to do that. We don't have to write all of that out. Instead, let's just jump right into finding this probability from scratch using the multiplication rule for dependent events. So what does this look like? Well, when we go into the deck and we go to pick a jack, there are, of course, only 4 jacks out of 52. But if we go to pick our second jack, we have put 1 jack into our pocket and we're left with 51 cards in the deck and only 3 jacks. Again, when we go into the third time, we now have 2 jacks in our pocket, which means there's only 50 cards left and only 2 jacks there. Which means without having to write all this blue highlighted stuff, we can get right into it. We can write out these fractions in the multiplication rule and get our probability of 0.002. So as you would expect, this is a very low probability of selecting 3 jacks in a row in a 52 card deck. Let's look at another example. A bowl contains 4 red, 3 green, and 5 white cubes. Find the probability of selecting a white cube and then a red cube without replacement. Okay, so what do we got here? We got our without replacement means that we have some very nice dependent events. We also can label these events with a capital letter. W would be white cube, R would be red cube. We know we're using the multiplication rule because we're picking successive cubes here. So therefore, we're finding the probability of W and then R, which according to the multiplication rule for dependent events, it's going to be the probability of selecting white times the probability of selecting red on the second turn, given that they selected white on the first. Okay, what does this look like? Well, selecting white, we need to know how many total cubes there are. You're just going to add 4, 3, and 5 to get 12. And out of those 12 cubes, which is our sample space, we're trying to find the probability of the event white occurring. Well, that has 5 options for 5 white cubes. Next, what changes from the problems that we've done cubes with before? Well, now we're taking that white cube and we're sticking it in our pocket. which means the bowl has now changed. Its probability has been affected because now there's only 11 cubes in the bowl. So when you go to select a red, we have to say, well, how many red cubes are in those 11? Well, we didn't mess with the red the first time. It was a white, which means there's still 4. So we're getting 5/12 times 4/11, which is about going to be 0.15 repeating. So what about a green, green, and then a white? So 3 of these this time. Again, let's get away from the formula. Let's just jump right into it and see how this works. So if we, on our first grab into the bowl, there's 12 cubes, and we're trying to pick a green one. So there's 3 of them the first time. So then we take that green cube, we put it in our pocket, we go to reach in the bowl again. There's only 11 cubes in there now, and there's only 2 green because there's 1 in your pocket. Now there's 2 in your pocket, 2 green. We go to reach in the bowl, and there's 10 cubes left, but we never picked out a white before, so there's still 5 of those in there. So if we put this together, we get a probability of 0.0227. Just to mention, hitting the pause button for a second here, the most common error on all exams when it comes to a problem like this is to use the addition rule instead of the multiplication rule. As soon as you see something about replacement, then you should know to use the multiplication rule. Replacement has nothing to do with the addition rule, and the addition rule always utilizes the word or because you're picking one thing and you're trying to determine if it's something or something else. Whereas with the multiplication rule, you're picking multiple things in a row and you're trying to find the probability of that occurring. Okay, last problem. We're going to go in kind of a word problem type of avenue here. It says, a committee consists of 6 women and 4 men. The committee will randomly select 3 people to attend a conference in Hawaii. Find the probability that they are all women. A good way to interpret this would be as follows. We're out of these 10 people in the committee, we're trying to find the probability that we will randomly select a woman, and then another woman, and then a third woman. So as you can say, just by the way I said it, this is a perfect example of the multiplication rule of basically 3 things in a row or 3 events in a row. We could call them W1, W2, W3. That's fine. We don't need to do that. We can do it just like this and do the math, for example. When you go to select the first person, there's 10 people in the committee. That's your sample space of people. But the event of picking a woman, that would mean there's 6 out of them possible. Now, it's really important to note here that once that person is selected, they're probably throwing a party. They're going to Hawaii, right? So they're running out of the room and probably into the parking lot because they're so excited, or somewhere. So what does that mean? That means that in this scenario, we're talking about dependent events because we don't replace the person after they've been selected. Nowhere in here did it say anything about replacement. That's because it's insinuated in the problem. You're not gonna pick a person twice, which means once you pick the person, they're gone. They're not a part of it. They already are going to Hawaii. Now you need to pick from the remaining 9 people for the probability. So the second time when you go to pick a person, there's only 9 left. But this time, one of the women has already been selected, so that means there's only 5 left. Along the same lines, once 2 women are now going to Hawaii, then there's only 8 people left total, and there's 4 of them that are remaining that are women. So the probability of selecting 3 women in a row is going to be 6/10 times 5/9 times 4/8, which will be approximately 0.1667 as your resulting probability.